Well, good evening. On behalf of the members of and friends of Countryside Community Church, we want to welcome you this evening. This has been a long time coming. We had invited Lucianne to come and speak with us a year ago, but she got snowed out. So this year she graciously came a day in advance and hit the great weather last night, I'm sure. But very much looking forward to this. You know, years ago I did a calculation on just the number of stars in our solar system. I mean, not our solar system. Already looking stupid in front of the scientist. In the Milky Way galaxy, and that number has risen over the years. It started out, my first number I heard was 100 billion, then I heard 200 billion, and then I've heard speculations it could be double that, or I imagine we'll hear more about that tonight. But just at the basic 200 million level, I wonder, well, how many is that? What would that look like? And I thought, well, what if you had a can of Morton salt, and like every grain of salt in the can represented a single star in the Milky Way. So I did research online, figured out, how much the Morton can weighed and how many grains of salt could be in and all this. Do you realize that if you were to represent our Milky Way galaxy, every star, bear in mind our sun, which is 100 million times larger than the Earth, and that's like a medium-sized star. If every grain of salt represented a star, you'd have to have 76,000 cans of Morton salt. Kind of, blows my mind. And just what are the what are the chances of some of those places being habitable? Now that thanks to the work of Dr. Walkowic and others, just really opens up the imagination. And some people think that's a challenge to faith. Like, if we're not the only ones, somehow we don't matter. But just imagine being able to look out at the stars and coming to some sort of deep realization that there's a whole community. We're just in the midst of this huge community of the universe. I don't know. I can't imagine how one's faith could be challenged by that, but rather the awe and wonder of it all and the life that's out there. Anyway, you didn't come to hear me speak about the universe. I just wanted to introduce or welcome you, and also note that for those of you who are first-time visitors, we would want to especially welcome you to have some conversation and cookies afterwards if you go out and make a left into the commons, and also if you make a sharp left, you'll find the bathrooms there as well. And if you happen to have one of these in your pocket, if you wouldn't mind either turning that to off or stun or whatever it takes to make it not ring, that would be really gratefully appreciated, especially by our speaker, so we don't interrupt her. But let me bring forward, without further ado, the director for the Center for Faith Studies, Kelly Keller, and she will introduce our speaker.
Thank you, Eric. And thank you all for being here. I'm sorry, Lucianne. I'm sorry that you had the turbulence yesterday coming in, but I'm so glad it was yesterday and not tonight. And I'm so grateful to have you here. We are so pleased to have you with us this evening. The Center for Faith Studies, for those of you that aren't familiar with the Center for Faith Studies, we've been in existence for going a little over 11 years, and we just explore these ideas. We know that to be a faithful people of God, we need to explore the world that God created. And so we want to know the best of science and the best of the humanities and theology to really understand this world that we live in and how to best live fully in it. This season's theme is the mythic journey, serving beauty and hope in an everyday world. And this theme really centers around the idea that it's not hubris, it's not foolishness, it's not naivete to believe that our lives matter, even among all these billions of stars, that our lives matter. And the idea that life is precious, it is ours, let's live it. Peter Pan says, it would be, to live would be an adventure, right? So we're buying into that tonight. And Dr. Walkowic is such a great person to have for this theme. What can be more mythic journey than space travel, right? You think of Star Wars and Star Trek and all of the ideas of rocket ships. As part of her lifelong explorer status, she holds degrees from Johns Hopkins University, and a master's degree and a PhD from Washington University, and she's been at Berkeley and Princeton. And I'm saying all this because when she steps up here, I already know what you're going to say. She's a kid. She's very young looking, but she has definitely a pedigree of education behind her. She's on the staff at the Adler Planetarium, has been a TED Fellow on the Kepler mission. She's a leader in the Large Synoptic Survey Telescope, which I found out more about today, which has been a journey of love for you over the last 7 years. But even more than her pedigree, Dr. Walkowic is definitely a person who has decided to live life. She is not only this brilliant scientist, but she's this creative soul. She started by wanting to be a comic strip illustrator. And she became this amazing astronomer. But the comic strip illustrator is still very much a part of who she is and how she relates to the world. And she has taken art and music, and she just doggedly, I think, expresses the belief that science, art, and the imagination can do wonders for the human experience and for engaging for a better world. And she does that with life and energy. And if that weren't enough, I said this morning to her, is there anything cool you don't do? As I found out that she surfs in places like Costa Rica and wherever, England and Chile and other kinds of places. So she's a surfer too. So she's, my hip level went up a little bit just by being around her. So please, I'm so excited to have her tonight with us. Please help me welcome Dr. Walkowic.
Well, thank you so much for that wonderful introduction. I'm probably blushing at this point. Can everyone hear me in the back? Great, wonderful. Well, thank you so much for having me. This is my first time in Omaha, and actually my first time in Nebraska, although I actually know 2 astronomers from Lincoln, somewhat improbably went to high school together and eventually became astronomers like myself. So I wanted to talk to you today about a variety of different topics. Just broadly, we settled upon the title of Planet Hunting, Looking Up, Seeking Life, and Finding Home. So I'm going to speak a little bit about the research that I do and our literal place in the universe. But then I also want to talk a little bit about how we as human beings connect to the universe. So I really loved growing up this comic strip, which, if you're not familiar with it, this is Calvin and Hobbes. It's the adventures of a young boy and his stuffed tiger, who is actually, to him, a living character. And so they're talking, and they say, Calvin says, if people sat outside and looked at the stars each night, I bet they'd live a lot differently. And Hobbes says, well, how so? And he says, well, when you look into infinity, you realize there are more important things than what people do all day. Which I think is kind of a nice way of thinking of it, although that actually is what I do all day. Most of the time, it doesn't look very, it looks kind of like what it looks like to you right now. I go around and I do research with half of my time at the Adler, and then the other half of my time I spend doing public communication of science, either via this way or through interacting with our guests in the planetarium. Like 90% of the time, it looks really boring like this. This is me. I actually realized, like right before this talk, that I'm wearing the same shirt. This probably looked exactly like that earlier today, actually. So usually, like the glamorous life of an astronomer is actually not that glamorous. It's a lot of looking at my laptop. But I do get to work on some pretty cool stuff. And in particular, I get to work on literally our place in the universe on planet Earth. And so I wanted to sort of start out just telling you a little bit about my own personal journey, which is that I didn't really grow up looking at the stars. So many of my peers, including the 2 astronomers that I know from Lincoln actually, had the benefit of a wonderful night sky that they could see. You know, many of my peers have these stories about, you know, having a backyard telescope and going out and stargazing. None of that. I'm from New York City. You really can't see very many stars in New York City because we have a very bad issue with what's called light pollution, or light that is directed upwards into the sky where it blots out our ability to see the stars. And so, you know, usually this is like a pretty typical New York City starry night sky, which is to say that there are no stars. The city lights are themselves beautiful, but they're not really the majesty of the heavens per se. And you know, I had actually looked up. It was part of my experience to go outside and look at the sky, but you know, there was really like nothing to see up there except for the moon occasionally. But on a family trip in when I was 14, I guess, we were driving across country through Arizona, and I had the opportunity to see this night sky for the first time. And this is actually taken in Arizona at the Lowell Observatory in Flagstaff. Obviously, this is a little bit more intense than what you would see with your eye because it's taken with a long exposure photograph, but it's not that much more than you'd see with your eye. If you've ever had the opportunity to see a really dark night sky, either in the general vicinity of here or in somewhere that's really dry, like Arizona or on a mountaintop somewhere, you know that the sky is so full of stars that it's, you know, if you're somewhere really dark, it can be actually kind of hard to make out what isn't covered in stars. And it's really a beautiful and arresting thing. And it's, you know, it's the basis of a lot of, you know, this is the mythic journey, right? It is a basis of a lot of our sense of where we are in the universe from the time that people told stories to one another. It's, you know, where navigation comes from. Our ability to view the night sky is deeply tied to our experience and our history as human beings. And so I had looked up, but I had never actually really seen what the night sky truly looked like. And I felt a little bit robbed, honestly, when I finally saw what was up there. But, you know, I went right back to growing up in New York City and fell backwards into astronomy just because I liked science when I was in high school. And I wanted a way of combining physics and chemistry together. But, you know, now that this is actually what I do all the time, you know, I'm constantly butting up against this idea that, like, you know, space is the final frontier. We see it in fiction and we see it in movies, and it's out there, and it's sort of a crazy, you know, wild west of a place. But it's also, you know, our home. And so when I talk about our work with Kepler and finding planets around other stars, I always really like starting with our home, the Earth. So, you know, when you're an astronomer and you work on finding planets, people ask you what your favorite planet is a lot. It's just a thing. Mine is Earth, for the obvious reason that we live here. But also for the fact that, you know, a lot of the search for planets in the universe is about finding planets that are like Earth. Because a lot of it is driven not by finding the planets themselves, but by finding places that we might actually look for or discover life elsewhere beyond our solar system. Or frankly, even within our solar system on some of the other planets or moons that are here. And so, you know, it's worth bearing in mind that literally for the entirety of human history, with the exception of like the past 25-ish years, this has been the only planet we knew about, like the Earth, for basically the entire time. You know, a couple centuries ago, we sort of figured out that there were other planets within our own solar system. And now we, you know, count these 8 major planets of our solar system and then countless other dwarf planets. Even our own solar system is, to a certain extent, somewhat undiscovered. You know, just today, actually, we were speaking just beforehand about the fact that there was another dwarf planet or a big icy thing, sort of similar to Pluto, that was found very distant reaches of the solar system. And so the outer solar system is still largely undiscovered in its own way. But nevertheless, this is still, you know, this is the equivalent of knowing the other houses that are on your block. Over the, you know, history of astronomy, we've, you know, and certainly the development of the telescope, we've now come to understand that our sun is really just one of many stars within the Milky Way for sure, but also a star that is a member of what we call a solar neighborhood, or stars that are just in the general vicinity of our sun, many of which we now understand to have planets. Even even the ones that we have not discovered yet, what we know now from the commonness of planets is that there's probably one within about 10 light years, so, not exactly next door, but, not, not totally beyond the universe from us. And so we do have this sense of now being in something of a solar neighborhood that is populated not just by stars, but by planets as well. But as I speak about the planetary discoveries that have happened over the past very few years, keep in mind that this is actually a very small fraction of our galaxy as a whole. This is obviously an artist's conception. This is our Milky Way as it would look if we could fly outside of it. And really just this little circle that's drawn there around the sun is the regime in which we've been able to find planets so far. Even the ones that we found in large quantities over the past couple of years come from a very small fraction of space. And so it's an amazing thing, actually, that because of the way the Kepler mission was designed, we can now say that there are likely to be billions of planets in the galaxy as a whole, even though we haven't found all of them yet. More on that in a moment. So I do want to speak, I've mentioned Kepler a couple of times, but I want to speak a little bit about how Kepler worked and kind of how it's changed what we know about Earth's place in the universe. So Kepler is a space telescope. I will show you a picture of it momentarily. It launched back in 2009, but it was a labor of love for the project team who made it happen for easily a decade prior to its launch. But actually for its principal investigator, Bill Barucki, he suggested, let's see, roughly almost exactly to the day, I believe 25 years before the mission launched, he published a paper that said that you could launch a space telescope that would measure how bright stars were and that this would be really great for finding planets. Everybody said, Bill, that's ridiculous. At the time, they were actually correct. It was ridiculous. The technology was not good enough. But, technology changes and catches up. And eventually it became a plausible thing to be able to make the kind of measurement that I'll tell you about that's allowed us to find planets around other stars. I had the great benefit of joining this, right before the fun began and after all the hand-wringing of whether it was going to happen was over. Except for this one moment that I'm showing you a picture of. So this is the evening of the Kepler launch before it happened. This is a picture taken at Kennedy Space Flight Center. Roughly 2 weeks before Kepler launched, another mission that was intended to study the atmosphere of Earth was launched, and they go up in sort of these compartments in the tops of rockets. There's supposed to be a bolt that explodes, and then the spacecraft goes to space, and then the rocket comes back down. If the bolt doesn't explode, everything comes back down. And that's what happened to that spacecraft, which happened to share the exact same part that failed with the Kepler launch vehicle. So this was a very fraught launch. We were very scared. So I am smiling, but I'm actually quite nervous in this picture. But we had a beautiful, successful launch. And this was really the beginning of a journey from 2009 until now that has informed what we know about planets in the universe, and specifically what we know about planets that might be like Earth, the places that we might look for life. So this is what Kepler itself looks like. I often say it looks like kind of like a gold lipstick in space, albeit much bigger. It's about bigger than a phone booth, roughly. And it was designed with this very specific goal, which was to look out into space and use this particular method called the transit method, which I'll tell you about momentarily, to figure out how common planets the size of Earth are around stars like our sun. Amazingly, even though the mid to late 90s was when we first started to find planets around other stars, the planets that we found first were more similar to Jupiter. And even those planets were actually quite dissimilar from Jupiter, but they were sort of large balls of got that weren't really the kinds of places that we would expect to find life in the universe. And for reasons I'll describe, the planets that are like Earth are quite small. I mean, the Earth seems very big to us, right? But actually, in terms of being able to detect them, it's very difficult because planets are literally billions of times fainter than their stars, and so you have to be a little bit sneaky and figure out ways to use the star to help you detect the planet. And so this was a very basic question, which was not, it's not where is the most Earth-like planet in the entire universe. It's not where's the closest. It's just how common are they? So in this sense, Kepler was a statistical mission, not designed to find every planet in the sky, or even the ones that we could study the best, but just to figure out how common they were after all. So Kepler used this method called transit photometry, or just the transit method for short. And if you could watch this happen in our own solar system, which you can, every once in a while, Venus transits in front of the Earth, in which case you would see something akin to this little cartoon that's up here, where you literally see the surface of the star, and you see the planet pass in front of it. Now, unfortunately, most stars are so far away that, with very few exceptions, the sun is the only star that's close enough to us that we can actually see its surface. Every other star in the universe essentially looks like what we call a point source, or just a bright shining light that's far away from us. And so instead of being able to take an image that looks something like this, what we get instead is what we call a light curve. So what Kepler does is it makes these very, very precise measurements of how bright the stars it looks at are with time. And it looks for that planet to pass in front and block some of the light from getting to us, and that makes the star become fainter just for a couple of hours. And so what we get back is not these beautiful images that, if you're a fan of space, maybe you've looked at pictures from the Hubble Space Telescope. Images from Kepler are not very attractive, but transformative in their own way. Now, the thing that made it so difficult to figure out whether there were planets the size of Earth was that basically it's just like if you're in a movie theater and somebody walks in front of the screen. A big person is going to block more of the screen, much more noticeable. A small person or a child is going to run in front of the screen. They block much less of the screen, much easier to ignore, much easier to miss. Now, in the case of planets, if you have something like Jupiter, so Jupiter is about 1% of the area of the sun. And so it blocks, as I'm showing you here on the left, it blocks a fair fraction of that light from getting to us. The Earth, on the other hand, you could fit, so if you were just taking an image of the sun as I'm showing here, you could fit 109 of those Earths across the face of the sun. And so that means that a very, very, very small fraction of the light from the sun is blocked by a planet that's the size of Earth. And this morning when we were speaking about this, the analogy I like to use is that if you were Kepler, it's a little bit like your job is to sit across a football field's distance from car headlights, and you're supposed to see whether a fly has flown in front of those headlights. That's your job. So it's a tough job. And this is why these small planets that are potentially like Earth really eluded us for so long. Now, if you have, I was showing you in sort of cartoon form, but again, we get these measurements of brightness with time, or light curves, where if you have a larger planet, you get this sort of largish dip in the light, and that signal that you're looking for is very difficult to see if you're actually looking for a planet that's a lot smaller. So the smaller the planet is, the more difficult it is to find, really. I actually have a bumper sticker hanging on my fridge at home that says good planets are hard to find, which is a good way of thinking about the Earth, too. Now, I've mentioned that we want to find planets that are like Earth, or that are good hosts for potentially life in the universe. And usually the way that we do this, because these planets are far away and they're difficult to understand in detail, is we look for, first of all, these small planets. Keep in mind that our own solar system is very much like the Rosetta Stone of how we understand other planetary systems. So in our solar system, and this is not to scale, but we have these small rocky planets that are in the interior, pretty close to the sun, and then the exterior of the solar system is dominated by these large gaseous or icy objects. And so we don't think of those as having like the chances, there's not even really a surface to walk around on. So we think of places like Mars, Venus, and Earth as being the kinds of places where we might find life. So this is why our only example of life really informs what we go looking out in the universe for. We also reside at this one particular distance that allows us to have enough warmth from our parent star where we get enough warmth that we have liquid water on the surface. And so to a certain extent, a lot, and NASA's motto actually for finding life in the universe has been to follow the water. It's not that we don't find life elsewhere. We certainly find life in lots of crazy places that human life would immediately expire. But we find that life thrives in the presence of liquid water, and so very much there's a search for finding places that are the right temperature. And the way that we understand that is how far the planet is from its star. Now, if I show this for comparison, not every star is like our sun. Our sun is a fairly middling-sized star, not too hot, not too cold. And if I sort of line up the solar system in cartoon form here by distance, and put it next to our star, you can kind of see that Earth is in this little parallelogram of blue that shows you roughly where the temperature is right to have liquid water on the surface. Now, there are many stars in the galaxy and many stars in the universe, but that distance that you want to be away from your parent star changes depending on how much light is actually being put out. So let's say, for example, that you have many hotter, brighter stars that you want to find planets around. That means that you have to look further away, so that blue stripe sort of moves out and away. This is equivalent to if you had a really blazing campfire, you would want to be further away from it to be the right temperature. If you sat the same distance as you would for a smaller campfire, you'd be too hot. On the other hand, if you had something that wasn't glowing with as much energy as our sun puts out, then you would want to be a lot closer, right? So if you were just down to your glowing embers of your campfire or your fireplace, you'd sit very close in to get the same amount of heat. Now there's a sort of catch to this, which I'm not going to talk too much about, but you can ask me about afterwards if you like, which is that actually these cooler, dimmer stars, these red dwarfs is what they're called, these are the most populous kind of star in the galaxy. They actually make up 70% of all stars, but they're so faint that you can't see any of them with your naked eye at all. So even if you go to a really, really dark place and you see the sky full of stars, you still can't see 70% of them, just because they're too faint, not because of light pollution, which is kind of crazy. It means there's really a lot of stuff up there. Now, the neat thing is that they actually have planets that are similar to Earth in terms of their size, just as commonly as stars like our sun. And that means that the solar system might be a little bit of a weirdo in that we have this sort of yellow middleweight star instead of this little red dwarf as our planet host. So that's sort of a neat thing to think about, I think. But I've been assuming that we all want to find planets like Earth, and sort of taking that as a basic underlying tenet. But you might fairly ask why we should care. And in particular, sometimes I think people get the idea that astronomers are just not very creative. Sort of like, oh, why are you always looking for things that are like Earth? Well, again, it's because we have only one example of life in the universe. But really the reason that sort of drives what we look for is that the distances of all of these planets are gigantic. Interstellar distances are huge. We really don't have a good way of efficiently traveling to other star systems. And so, actually going to these planets is a little bit beyond what we can do, certainly what we can do in a human lifetime right now. So when we look at any of these planets, we have to be able to understand whether they're either habitable or inhabited from afar. And that means understanding how a planet is changed by the presence of life on it. So because we're working from our one example, which is Earth, we have carbon-based life here, and we know, roughly how different forms of that life change our atmosphere. Certainly, plants breathe in carbon dioxide, human beings breathe in oxygen and breathe out carbon dioxide, and we have this relationship between us and the other life forms on the planet that results in our atmosphere being the makeup that it is. Before the rise of these little blue-green algae, there actually wasn't a lot of oxygen on Earth. And so, you have the very lowliest creatures to thank for the breathable oxygen that you have today, plus the complicated plants that keep it that way. So if we want to be able to look at these other planets and understand whether they have life or whether they'd be good for life, a lot of that is about looking at what the atmosphere of the planet is made up of as a whole. Now, it doesn't mean that there can't be other situations out there. Certainly, even here on Earth, we thought there would be nothing at the bottom of the ocean until people sent submersibles down there, and lo and behold, it's not just a bunch of boring bacteria, no offense to bacteria, but there's some very exciting looking shrimp that live down there by by the deep sea vents where they get absolutely no sunlight. They get all their warmth from the internal heat of the Earth. And that's, that's so far under the ocean that it was not, observable by us on the planet. So, there's certainly other possibilities out there. And even, Kelly and I were talking about other exotic forms of life. And couldn't there be stuff that isn't carbon-based? And so that's why, for those of you who like comic books, as you know I like comic books, this is the Thing from the Fantastic Four. He used to be a carbon-based life form, and then through a horrible accident became a silicon-based life form or a thing made of rock. So silicon actually sits right under carbon on the periodic table, which means that it's formed similar kinds of bonds. But actually, there's a lot less silicon in the universe to make up stuff out of. And that's just because stars are responsible for producing a lot of those heavier elements. And so they make more carbon than there is silicon. So the chances are actually pretty good that life out there is carbon-based. But again, who knows? We get surprised all the time. Scientists actually do like being surprised. But chances are the life that we recognize first will be not too terribly dissimilar. So to return to Kepler momentarily, I'm going to tell you a little bit about what Kepler found, but just a little bit about how it did its mission first. I mentioned that it did this planet hunting with the transit method, where it looked for that light to be blocked and dim for the star for just a couple of hours. Now, because it was trying to figure out how common these planets were, the first thing you have to do is you have to look at a lot of stars, because if something is rare and you don't find it because you only looked in a couple places, then you don't actually get to figure out how common it is. You just know that maybe you didn't look in enough places. So Kepler looked at roughly 160,000 stars in this one patch of the sky. It made these very precise measurements. Its ability to measure how bright the stars are with time was very much enhanced by the fact that it went to space, so there was no atmosphere to create twinkling or uncertainty in the brightness of those stars. The mission lasted several years, so if you think about, if you were outside of our solar system and you were watching for the Earth to go around and block some of that light, you'd have to wait a year in between, right? Because that's how long it takes for the Earth to go around the sun. So, you want to be able to measure these signals and see not just that they happen once, but that they happen again and again, because the length of that year is actually related to how far the planet is away from its star. So that's how you figure out how much light it's getting from the star, and therefore whether it's in this sort of Goldilocks, not too hot, not too cold zone. And it also stared at this one part of the sky without interruption for many years. This is the part of the sky. This is sort of the end of the season of being able to see it because it's up in the summer. But it's roughly about the size of your hand held out at arm's length. So actually a relatively small part of the sky if you think about trying to spread your hand all over the entire sky. So it was mostly just chosen because it had lots of stars in it, not too many. This is an image from Kepler. So you just sort of see those little rectangles are the detectors, very similar to the kind of thing that is in your phone that takes digital camera pictures. These yellow dots are the 3 planets that were known before Kepler launched. So other missions had found that there were planets around there, but after Kepler had been operating, I think this is about a year and a half in, it went from looking like this to looking more like this. So this is called the Skittles plot by the team, for obvious reasons. The different flavors are to do with how big each one of these planets are. And you can see that there are lots and lots of orange and red things here, and then fewer, but still Earth-size and super Earth-size planets. So super Earths are just things that are bigger than Earth and smaller than Neptune. So this was actually, I think, only about 2011, so this is only about a year and a half into Kepler's operations. So this was kind of an amazing and transformative mission in the sense that we went from not really being able to find very many planets that were small at all to being able to find lots and lots of planets of all sizes. The reason that there are so many red and orange dots here for those big planets is actually just that they're easier to find. Like, they're totally a piece of cake for Kepler. It takes a little bit more work to be able to detect those little small divots from the Earth-sized planets, but they are certainly, even at the beginning of the mission, we were already doing that. And now there are more all the time. So this was really kind of an amazing thing. Now, to figure out how common those planets actually are, what you want to do is figure out what did you find? So, how many of the very large planets, how many of the middling-sized planets, and how many of the small planets? And then you correct for what you should have been able to find. So if maybe some of you have caught me on this already, but if you're looking for a planet to block some of the light, it has to be lined up right? So if it's orbiting like this, it never passes between you and the star, and you never actually see the star get dimmer. Fortunately, this is actually just pretty simple geometry. It just has to line up pretty correctly, and the assumption is that there's no preferred way for it to be oriented towards you. So we know that the planets that we find are only actually a small fraction of the planets that are out there, and that's one step in figuring out how common planets are overall. Now, when you make all of these corrections, the amazing thing that you find is that even though there were a lot of colored dots that showed you where big planets were in that previous plot, this is sort of towards the end of Kepler's main mission. When you correct all of them, what you find is that actually the most common kind of planet that the universe contains is these small planets, things that are about the size of Earth to a little bit bigger. Not all of them are in this habitable zone where you can, have the right temperature conditions for liquid water, but many of them are. And perhaps even just as confusing is that there are also actually in equal proportion pretty much these super-Earth type planets. So this is another way in which the solar system is a little bit of a weirdo, is that we don't have any planets that are between the size of Earth and Neptune. Like, we have Neptune, and then we have the Earth. And so these super-Earths are somewhat mysterious to us because we don't really know whether to think of them truly as like a super-Earth, like it's just a blown-up bigger version of Earth, and it's a place that might have oceans or continents, or is it a tiny version of Neptune? So in other words, mostly just gas and ice, and not a place that we would look for life. And so super-Earths have gone from being something that we didn't even know existed to being something that's a really active area of study so that people can try and understand whether these are also places to consider for looking for life in the universe or not. So it's sort of an interesting thing that, it's very rare that you can say in just the past, 6 years, you've gone from not knowing whether there were any planets the size of Earth to knowing that they're the most common thing in the galaxy. Pretty cool. Usually astronomy takes a long time. So this is really a transformative result, and it's very exciting. Or at least I think it's exciting. If you're a follower of this at all, you'll notice that there's lots and lots of headlines. These are just some random headlines grabbed from different publications about, like the nearest planet and the most Earth-like planet ever, and it's Earth 2.0 or 3.0 or whatever it is. I love each one of these things, and I love the art. This is an artist conception that goes with it. They're always very imaginative. There's all kinds of, basically what I've told you, right? Now you know how the sausage is made. You know that we basically know how far it is from the star and the size, right? And that's kind of how we're inferring whether it's likely to be habitable or not. But when you see artist conceptions, of course, they have beautiful continents and atmospheres and liquid water, which is great. Astronomers like to imagine these things too. And one day, maybe we'll be able to figure out these things, probably not too far from now. But these are two, if you work in the field, these are two science journalists that I follow on Facebook that I thought was very funny, where they coined exoplanet fatigue, where, it's almost easy to sort of let these discoveries wash over you, and it's like, oh, didn't they already find the most Earth-like planet? But, I hope you won't feel that way. We'll actually continue to find more and more about these planets, which I think is very, very exciting. So don't be, Kenneth Chang here calls my friend Lee an exoplanet curmudgeon, so don't be an exoplanet curmudgeon. To sort of step back from the actual science for a moment of what we've discovered, I'm not stepping very far back from the actual science because I'm about to quote somebody's PhD thesis. I think this is the most quoted line in a PhD thesis probably in all of astronomy that isn't like a scientific result, and it's mostly because it's quite poetic. So this is from Jason Wright, who's a professor now at Penn State University. And he says, of all of the topics of study in astronomy, exoplanets, or planets around other stars, hold a special place in the imagination, because more than stars, nebulae, or galaxies, they are places. And this is really true, right? It's that, all of those things that we see with the Hubble Space Telescope, they're beautiful, awe-inspiring, but it's really that the planets that we think about, they're places. They're places that we can imagine ourselves. They're places that we can imagine other people. This is a grab from Star Wars. And that's Luke Skywalker walking out onto the desert vista of Tatooine and looking out at the 2 stars that are setting in the sky. This is from 1977. A couple years ago, Kepler discovered that actually it is possible for planets to form and orbit around 2 stars. So somewhere in the universe, there might actually be a Luke Skywalker walking out there and looking at the double sunset on his homeworld. And these are, they're not tremendously common, but they are out there. And so, we imagine these planets and we do those artist conceptions because they're very much about imagining ourselves and imagining those spaces. And so I think that this is why, more than anything, more than like finding aliens or anything like that, it's why people pay so much attention to the search for other Earths. And, like I said, it's, we're always sort of, scientists, loath to say that we live in a particularly special time because it smacks of like being, human exceptionalist or something. But actually, in the case of exoplanets, we do actually live in kind of a special time where just in the past 6 years, we went about not knowing this very fundamental question of like, is there another planet that is potentially like Earth, to knowing that the answer is yes, there might be. We don't know yet whether these planets are actually like Earth. The lesson from our own solar system is, of course, Venus. Venus is about the same size as Earth. It's not that different in its distance away from its parent star or sun, but it's certainly it's no place you'd want to vacation. It's like 800 degrees on the surface, very, very unpleasant place to live. But we wouldn't necessarily know that if we just detected something that was similar to Venus with something like Kepler. So over the next several years, what you'll hear about is people being able to sample the atmospheres of these planets and to figure out, are they made of oxygen and carbon dioxide and the kinds of things that we find here on Earth, or are they made of, nastier stuff that we wouldn't be able to breathe. So this is really actually kind of an exceptional and exciting time. Probably at some point we'll all look back and be like, we were so ignorant then. But that's great. That's how it's supposed to work. So I want to transition a little bit from our place in the cosmos, at least scientifically and literally speaking, to talking a little bit about how we connect to the night sky and how we connect to our knowledge about the universe. And I'm going to touch on kind of 3 things. One is just the very act of viewing the night sky, so a little bit back to the beginning of this talk. I'm also going to talk a little bit about participating in research and actually have a hand in that as just an interested person. And also at the end a little bit about experiencing science through art. So, as Kelly pointed out at the beginning, it is certainly something that I feel very strongly about, that science, although it has a reputation for being something that sort of happens off in an ivory tower, science is very much, a human product in the same way that like literature or art is. The fact that you don't necessarily encounter like science engraved into a plaque on the side of a building does not make it any less yours than the works of great artists or writers. And so I think that it's important to be able to access the products of science and to feel some ownership over it. So one of the things that I think is really important is I do actually think it's quite important to have the experience of viewing the night sky directly. We're now aware over the past, century or so, maybe even a little bit less, that our natural spaces are places that we should preserve. We don't, necessarily build into national parks, right? And so we don't think about the places that aren't, downward directed, that aren't the Earth. We don't think about the natural resource that is our sky. It has this place in human history. It was responsible for our ability to navigate the globe. It is responsible for much of our understanding, our stories, our myths. And so the ability to view the night sky, I think, is really, something that we all have a right to. And to a certain extent, so there are actually parks now. There are dark sky parks that you can go to. I wanted to make you aware of this website, darksky.org. So this is the International Dark Sky Association that do lots and lots of great advocacy for dark night skies. And there's also, it's past now obviously, but International Dark Sky Week happens usually in the spring every single year. And this is a time when you can appreciate, and I'll even show you a little project that you can do if you're interested, which has resources for it on darksky.org. What darksky.org does is they do a lot of advocacy around this issue of light pollution, the ability to access the night sky. So a little bit about light pollution. You know, this sounds sort of like almost like a fringy, like why would I care kind of issue. Like, oh yeah, okay, it's nice to be able to view the night sky, but like we need to be able to walk down the street without bumping into a pole. It's fair enough. To give you some idea of what the effects of this are, I'll tell you momentarily, but just broadly, light pollution is any kind of light that is upwardly directed that interferes with our ability to view the night sky. This is a before and after of a blackout that happened. So you can see there on the left is sort of the standard of what that particular neighborhood looked like, and then even with just the lower lights that they have on in the house, little torch lamps, you can now suddenly see, again in this photograph, that there is the Milky Way above there. And lots of people actually during this blackout, this happened, I believe it's from 2003 in the Northeast. It was actually caused by a big solar storm. And a lot of people saw the Milky Way for the first time. So I think they sort of got that as a bonus of the extreme inconvenience of having a large portion of their power grid go out. But this is something that we could actually experience if we were a little bit more thoughtful about our choices. So generally speaking, there's a variety of different terms for this. When we light something, what are we trying to do? Well, we're trying to make it safer, right? We're trying to see where we're driving, we're trying to see where we're walking, we're trying to see the area around us. Unfortunately, most of the time, our lighting fixtures are just sort of designed so that a lot of that light goes out either to the sides or even just above. If you think of kind of the iconic light bulb, right, or like a globe lamp that's just on a pole, a lot of that light goes in all directions, and a lot of that ends up being directed upwards. If it's directed upwards or if it's directed too far out, you have what's called either light pollution if it's going up, or light trespass, and you're all, I'm sure, familiar with this because this is where like street lamps end up going into your room and you end up having to close your curtains. You know, probably prevents you, at least in my last apartment, it prevented me from ever waking up with the sunshine because I had to always have the light blocked out in the evening, which was kind of a shame. Now, to a certain extent, this actually, even though the intention is to make it safer for us, it actually creates a lot of glare. So much in the way that you can't see very well when somebody shines a flashlight in your eyes, even though they're lighting up the area for you. A lot of that actually works against our being safer because of the fact that it directs light into our eyes instead of downward into the area. And in particular, it creates high contrast regions where there's very dark shadow and very brightly lit areas, and that can make it hard to see and make you less safe. The other reason that this is actually hazardous is that, you know, human beings, we grew up, we became the creatures that we are operating under certain circadian rhythms. And this has a lot to do with how we've been exposed to light. And actually, the exposure to light at night, particularly when you're sleeping, can be very hazardous to your health. So this is, I won't read this entire tiny text to you, but this is a statement for the American Medical Association from just 2012 about the fact that when we experience light at night and when it, you know, trespasses into our bedrooms when we sleep, even when we, you know, stay up with our computer screens and a lot of like blue light shining in our eyes late at night, it actually does disrupt your circadian rhythms. And, you know, it's not going to give you cancer, but the people that have shift work, for example, people who work graveyard shifts, actually do have increases in a variety of different cancers because this is so disruptive to the human body. And so, you know, I don't want you to leave, I would like you to leave inspired and not scared, but actually maybe check out some of the lighting resources that are on darksky.org. Because after all, you know, it doesn't have to be a costly solution. If you think about it, if you're sending light kind of up into the sky, that's light that's not being used by you, but it is light you are paying for, because that's the electricity is going up into the night to create this light that goes up into the night sky. And so to a certain extent, you might actually even save money. So this was a article from a couple of years ago saying that France on the Champs-Élysées, that they were going to turn down the lights. They were actually going to dim it at night. So rather than even replacing your entire light fixtures, you can also use things like timers, just so that the light shines when you need it and not when you don't, or the light shines where you need it and not where you don't. Because to a certain extent, what we really want is our light to be around us and to be working for us and not shining up into the sky. And that's something that we should think about now, because this is something where, as increasingly people live in larger and larger cities, a lot of children grow up without seeing a night sky. You're talking to one right now. And so this is something that I think is a real human right, and that's a real connection to our place in the universe and to our human history and the way that we've come to understand who we are. So just to give you some idea of how, if you are interested in any of the things that we've talked about today, there's another way of connecting with science, which is to become what's known as a citizen scientist. So I'll give you an example. This is, so the Adler Planetarium is the home to the web developers for a suite of projects known as the Zooniverse. So I'll show you in a moment what that word looks like, but it's like zoo and universe combined. So these are projects that you yourselves, if you should feel so drawn to it afterwards, can go and learn, take a short tutorial. They're really nicely designed, so they're very user-friendly, and you can actually help participate in scientific projects. You'll learn to make like a couple of different measurements. I'll show you an example here from Kepler momentarily. But this has been a real revolution in how people participate in science over the past 5 to 10 years or so. One of the amazing things that comes in particular from the Kepler-related citizen science project, which is Planet Hunters, or planethunters.org, is that these planet hunters, which you take a tutorial, it shows you, here's a measurement of how bright a star is with time, that's what those white points are, and you're looking, remember, for those little dips in the light, so you're looking for points where the star got fainter for a little while. And so you can learn what those look like, and you can mark them off. Some people get scared that they're going to be wrong, but it actually doesn't matter if you get it right, because many people look at each one of these. And so this really harnesses the power of many, many people working together to find these things. And one of the amazing things about the Planet Hunters project is that the Planet Hunters have found planets that were missed by the computer algorithms of the Kepler team. And so there's this now history and many, many examples from different citizen science projects of this kind of cooperation between the professional science community, astronomers like myself, and people who are making these measurements via these citizen science projects, where they've actually improved the overall ability of the professional scientists to do that work, or to improve their computer algorithms. And that's really amazing, because it means that everybody is working together to make that discovery more efficient. And there's people out there that are walking around whose sole motivation is that they want to participate in scientific research, who don't have science backgrounds. Like, you don't need to be a scientist. All you have to do is to want to do it. And this is kind of an amazing thing, to be able to say, yeah, I helped find a planet. Like that's water cooler bragging, like, for the rest of the year, easily. Like, I found a planet last night, MBD. In addition, what I think is really interesting is that not only are these people kind of connecting to the universe itself via this process of discovery, they're also connecting to each other. So this is an example from Planet Hunters Talk. This is just an online web forum. And there's a real vibrant community here of people that all work on the Planet Hunters project. And one of the interesting things that's happened sort of sociologically out of these kinds of projects is that not only do the citizen scientists go and do the thing that they learn to do, they're also just motivated by looking for cool things, right? So frequently, citizen scientists have discovered other things in the data that were, quote unquote, not what they were supposed to be looking for. and actually found like new kinds of galaxies or new weird things in stars. And this is an amazing thing because that's frequently, scientists come from a very formal background, generally speaking, where we're making an experimental design, we're looking to answer a particular question, and so there's a sort of laser focus to being a scientist and to doing a kind of science project where you're unlikely to serendipitously discover something new. That's just sort of built into the process. But because citizen scientists are just motivated by exploration and looking through the data in whatever way, they're not in a hurry to publish any of this stuff. This is like what they're doing when they're home and not at work. So a lot of times they make these serendipitous discoveries. And so again, you have this community of people who aren't necessarily from science backgrounds, but who are just interested in discovering things about the universe. So this is something that you can do too if you find this interesting. If you're really sick of space by the end of this hour, you can go to zooniverse.org, spelled like that, up there. And there's actually a variety of different things. So because I think about space a lot, my personal favorite is Snapshot Serengeti, which is motion cameras of animals on the Serengeti. Who doesn't like looking at animals? And actually it helps track how animals migrate and their different behaviors. So I highly encourage you to check it out if you're interested at all. So just and one more thing, which is that there is also a citizen science project that's related to light pollution. So during International Dark Sky Week, you can go out and figure out how many stars you can see. They pick a different constellation, generally speaking, every year. But you go out and see how many stars of that constellation you can see. And that helps you make a map of how bad the light pollution is in your area. And I believe there are exactly 0 dots in Nebraska, so if I come back, I expect there's this entire state to be filled in by next year, so that's your job. Maybe not the entire state, maybe just like a couple dots over Omaha would make me pretty happy. So you can actually help map out, what the condition of your night sky is. Maybe you could be the discoverer of a great new site for a new dark sky park, who knows? So just in the last couple minutes here, I want to talk about sort of the flip side of all of this, which is that, I did actually want to be a comic book artist at some point in my life, and I do still do art. Almost none of it is related to science, but sometimes it actually is related to science. So I wanted to show you some examples. Usually when you say you make art about science, people tend to think about very literal depictions. So again, back to this literal depiction of what this planet might look like, or there are people that do these hyper-realistic paintings like this. This is actually a picture of the floor of the Adler Planetarium in Chicago, where we have these like giant mock-ups of the solar system hanging from our ceiling. And that's really cool, and it's great to be able to imagine or have somebody paint for you what a planet might look like based on the best possible science available. However, I don't think that every depiction has to be really literal to be effective. And so over the past couple of years, one of the things that I've found sort of interesting to think about is that when you go to somewhere like the Adler or a different kind of science museum, planetarium, whatever it is, it's always very much about delivering information to you, right? Like kind of like the beginning of this talk. Like, here's a bunch of information about how we find planets and the things that we found. And that's great. But one of the things that I think art can do that's really interesting is, almost akin to the way that citizen science can allow you to participate in the scientific process. I think what art can do is convey some of almost the feeling or the experience of being a scientist. So I think about, what is my experience as a scientist when I look at my data? Well, the exciting part is when I don't know what's going on. The exciting part is not like, after I know all the things about the planet and I know what it looks like and what it's made up of. That's great and everything. But the exciting part is when I see something in my data and I go, what's that? I see a pattern, or I think I see a pattern, and I have no idea what it is. And probably the first 20 minutes of that are me being like, I probably did something wrong. I probably I'm gonna go back and make that graph again. So the thing that I wanted to do was give people an experience of experiencing like patterns in data directly. And this is something that is hard to do, right? Because generally speaking, the way that I interact with data is that a lot of my job is computer programming, and that requires learning to computer program. And so, there's sort of like a technical skill set that it would be nice to just circumvent if you want to give people the experience of detecting patterns in data. So I came up with this thing that looks like an igloo. Will not look like an igloo for the rest of the talk, I promise. But I came up with this installation called the Cosmos Room. So this was, let's see, about probably 12 feet high or so. So you had to kind of duck to get in the front door, but then you could stand up in it. These little mats that you're seeing kind of in the middle are mats, little yoga mat material mats. That were laid out in the shape of the Kepler detectors. And though there was some visual aspect and lighting to it, what this actually was a sound exhibition. So what I did was I take the measurements from Kepler. So Kepler measures how bright stars are with time. It looks for those little dips in light, but it actually also is possible to measure from the Kepler data how fast the stars themselves are moving. So stars actually spin on their axes like tops, and they have spots on their surfaces. And so that means that darker and lighter patches kind of rotate into and out of your view. And if you're looking at how bright the star is with time, that means that there is like a periodic frequency at which the star spins. In the case of our sun, for example, the sun spins on its axis roughly every month. Now, the catch to that is that stars aren't solid objects, they're gaseous. And so that means that rather than spinning like basketballs where everything goes around kind of the same speed, the equator of the sun goes around every 25 days, and the area near the poles goes around every 30 days. So there's kind of this like shearing, almost like a Rubik's Cube or something, that these stars do. Now that means that there's not just one frequency in the data, there's actually several. Depends on what latitude those spots are at. So you can see longer, higher, and lower frequencies in the data. And so I thought, well, how do you convey that? And what I ended up doing was figuring out what the frequencies were, and then just mapping them over to being sounds, and creating these sort of spacey sounding, basically sonifications, so taking what was actually visible data and turning it into sound. So here's kind of what it looked like inside. So again, here, this sort of orange print of circles you should recognize earlier as being the Kepler field of view, that thing that was about the size of your hand, now in a 12-ish diameter dome. And so you could go in, you could sit down on those like they were little mats, almost like meditation mats, and hang out. So this is myself and a couple of friends. I did this, we had a retreat for the TED Fellowship, so that's where it was. And I had, because human beings are very visual, I wanted to have something happening on the ceiling, so I had sort of these abstract looking, moving movies of starry looking things, but they're not really representation at all. So I'll play you a couple clips, just a couple like 15-second clips here and there. You should be able to hear them. That's one. There were also darker times in the thing, so this is probably a little hard to see. So one of the neat things about this was that it was very much like a meeting of the art and science, not just because I used the data for it, but the sounds were being generated. There was a little microphone in the room that I had wrote like some software in the same language that I used to like analyze my data. I wrote like a little program that would listen for noise in the room, and so every time it heard a noise, it would like trigger playback from this library. So it was sort of like a self cascade, and each one of these little clips would never recur in the course of you sitting in there. So you could sit in there for hours and hours and listen to this spacey music, unless you think it sounds terrible. Some people did. Most of them were too polite to tell me. But it was a way of, sitting there, and after a while you would hear, well, I hear structure, I hear patterns. but there was no explanatory plaque or anything like that. And so it was really having it was a way of having like an unmediated experience where you heard something but you didn't know what it is. Just like when I do my work, I see something, I don't know what it is, and that's exciting. Eventually this went up in a gallery in DC as part of this cool exhibit called Fermata, which was a big group exhibit of all these different sounds. Instead of having the meditation room type thing that we had in there, we had this speaker exhibit, so this is a very long, big gallery with this speaker wall. And so this had like 24 different channels, and you could just sit and listen or walk through the space and listen to it. And so, again, you can hear like the similarities in the sounds. So it's very good for your next haunted house. Yeah, so I hope you've come away with, I'll turn my art down a little bit. It's interfering with my ability to conclude. So, you know, I hope you've come away with some idea, first of all, that we scientists are not all just tied up in our graphs and our books, that, you know, we do actually think about how to connect people with the work that we're doing, because, you know, scientists are, I think, very passion-driven. You know, nobody goes into science for the big bucks. So, generally speaking, we're out there because, you know, we really do care about this process of discovery and about communicating with people and having, you know, you all feel some ownership over this as science as a human endeavor. So with that, I'll conclude and take any questions that you might have. Thanks.
So we do have some time for questions. I always need to start with the little disclaimer that we need to leave it to questions and not many speeches. And so we do reserve the right to kind of whip that microphone out of your hands if we're not hearing a question. But go ahead and raise your hand if you have a question, and we'll have one of our microphones get to you. I'll start here.
Hi.
Hi.
My question is about the exoplanets. Since it takes so long for light to travel from those places to Earth, I found it interesting that you talk about exoplanets as, you know, in the present tense, but what do you think has happened to those exoplanets, and how far away is that point in space, and what do you think has happened to those planets in the time that it's taken those images to get to Earth?
Yeah, so most of the Kepler exoplanets are about 1,000 light years away. So we're looking at light that's, you know, 1,000 years old or so. So, you know, if you want to figure out what might have happened, you can think about 1,000 years in the life of Earth. You know, certainly stars live for literally billions of years, and so, you know, those planets are probably still around. Things might have changed a lot. You know, certainly here on Earth, things changed a lot in the last 1,000 years. But to a certain extent, you know, it's impossible to know. The planet's probably still there, but, you know, if it has a civilization on it, who knows what the differences could be.
Hi, I noticed you didn't mention the wobble method of finding exoplanets. How much does that contribute versus the transit method?
It certainly did. Just to bring everybody up to speed, the wobble method is an alternative method for looking for exoplanets where instead of looking at the brightness of the star, you look to see how the star is moving as the gravity of that planet pulls on it. So this very, very tiny, tiny wobble. And so that's still used. It's still very productive. It's handy in that whereas the transit method tells us literally what the size of the planet is, the wobble method tells us more like how much stuff the planet is made up of or its mass. And so they're both complementary, and actually if you measure one planet with both of them, then you learn a lot. The thing that makes it less productive than something like Kepler is that it takes a very long time to build up enough measurements. And so it's very time consuming and it's very difficult to do. So it's productive and it's very helpful. It's just an alternative means, and it's not something that Kepler is capable of doing.
My question is on your sense of professional identity. Do you see yourself as an astronomer, an astrophysicist, or both, or some other things in addition?
Kelly and I just had a very funny conversation about this earlier. So amongst astronomers or astrophysicists, generally the two words are interchangeable. I have an undergrad degree in physics and a graduate degree in astronomy, so I guess technically you could call me an astrophysicist. But the running joke in the field is that astronomer is what you say when you want to keep talking to somebody, and astrophysicist is the thing you say if you want them to run away. Just because it sounds scary. And so I think I have business cards that say astronomer, and I have business cards that say astrophysicist, and I have business cards that say artist, and I have one that says astrophysicist and artist. The only reason I ever used astrophysicist was actually that I lived in Berkeley for 3 years, where a lot of people thought that I meant astrologer. And the thing is like, usually when people make that mistake, they're confused about the word, but they don't actually think you're really an astrologer, whereas in Berkeley, people are disappointed that you're not an astrologer. And that happened a couple times at parties, and I was like, I'm switching to astrophysicist, this is too depressing. So, but to answer your question for real, I think of myself as an astronomer and an artist. That's how I describe myself most of the time.
Okay, so there's all these planets out there that might contain life or might be like Earth. I'm very curious, have they stepped up the research towards developing hyperdrive and being able to travel at light speed to go visit one of these planets and see them firsthand? Like, is that possible, and like, do you believe it's going to happen?
It is possible. It's really hard.
Right.
So there's a guy... There's a guy at NASA who actually does study like making warp drive happen, but it's not prevented by physics, which is the good news. But it is like essentially impossible at this particular time, just because like you have to make like a giant Jupiter-sized ring of antimatter, which might as well be impossible for us. So the fact that it's not prevented by the laws of physics doesn't mean it will be impossible forever. But it certainly is at the moment. So right now, if you wanted to go to another planet outside of our solar system, people are talking about doing things like generation ships, where it would be like, hopefully not like WALL-E, but like a little bit like WALL-E, where you where you live. You're basically just on a cruise ship that's going to another planet like for the rest of your life, and hopefully like raising children that will eventually be who gets there. Yeah.
My question is, do you think we'll ever be able to find maybe a planet, a dwarf planet, that people can live on without air tanks or like Earth?
Well, that kind of goes back to the ability to travel to these other planets. Certainly in our solar system, Earth is the tops. We might one day get to live on Mars, but probably will, for a long time, be living in greenhouses essentially in order to live on Mars. Within our own solar system, there's not a whole lot of great places besides Earth for human beings to just sort of live on the surface and walk around and enjoy a beautiful day like this one. And that's why it's so important to take care of the planet that we live on. Now, if we get to actually travel to these other solar systems, then that might change things a bit. But in a lot of ways, we probably won't know very much about those places before we get there, and it might take hundreds of years to get there too. So definitely love the planet you have for sure.
Just a quick question about if I understand it correctly, the vast majorities of stars in the universe are red dwarf. The red dwarf types are much smaller, but those tend to have pretty significant solar flares, if I'm not mistaken. I just want to know if you could comment on the prospects of life around one of those, or we have to basically be constrained to the sort of main sequence yellow dwarf stars like our sun.
Well, so that's a good question because that's I'm biased. I think it's a good question because I work on that. These little red dwarf stars, as this gentleman has just stated, have the equivalents of solar flares on them, but as mentioned before, these planets have to be very close. That means that they get zapped with ultraviolet light and X-rays, in addition to the sort of regular red light that the planet gives off, or the star gives off. And so one of the things that astronomers like myself and my colleagues are trying to understand is, is that good or bad for life? To some extent, you might imagine that it wouldn't be so good to have like ultraviolet light or X-rays showered down upon you all the time. You know, you think about putting on sunscreen or getting an X-ray at the doctor, you put a lead coat on, essentially, right, to prevent that from hitting you. Now, on the other hand, you look at, for example, high-altitude plants here on Earth that are exposed to higher levels of UV, develop their own waxes that essentially they make their own sunscreen. If you look at the ocean, you know, the ultraviolet light doesn't get more than a couple inches into water. So maybe actually most places in the universe that are habitable, if you have water, maybe you want to live underwater instead. The only real reason that those kinds of stars would really be showstoppers for having planets that were potentially places that we could find life is if they, one of the things that can happen, and this is what happened to Mars's atmosphere, we think, is that they can strip the atmosphere off the planet. And if the atmosphere goes, there's no chance of having liquid water on the surface. You know, there's not enough pressure there, like water can't exist in a liquid state. And so that would probably be really detrimental. But we just don't know yet. And it makes a big difference, right? Because if 70% of all the places that we might look for life are not good places for life, then that's very disappointing. But chances are, I would guess that it'll be a mixed bag. Some places will be bad and some places will be good.
Focused on light, but we keep reading about all of the 85% of the universe that's dark matter. Mm-hmm. Does that come into play at all in your work?
For my work, I largely get to ignore dark matter. You know, so it is a sort of a crazy thing that most of the matter in the universe doesn't interact with light, and that's why it's dark. You know, it's not just that it doesn't shine; it's that it doesn't interact at all. For the purposes of, you know, looking for exoplanets or any of this stuff, I kind of work with things that shine, or at least that reflect light in the case of planets. So that's sort of something that I get to pretend doesn't exist out there. I leave that to my other colleagues that deal with the structure of the universe.
Hi, do you have a percentage of those 160,000 stars that you observed? Right, a more recent than 2011 percentage that would have the Earth-size or super-Earth-size planets that could possibly inhabit life? It
kind of depends on what kind of star they are. So, and I think with the little red dwarfs, it's sort of 50%, and I think it's a little lower than this for the stars like the Sun, but not by a lot.
Yeah. You said that there couldn't be any liquid water on Mars. I thought, like, in CNN last month, or a couple of weeks ago, I think, they had something about how there was, like, liquid water on Mars. It was just, like, very, very salty and briny.
Yeah, so the liquid water that's on Mars is in these streaks where it's sort of, we don't really know what the source of it is, but it seems to come out and, like, run down the hillsides there, but not in large quantities. And it disappears almost immediately because it can't exist in like puddles, for example. So there is liquid water on Mars, but there's not like vast oceans on Mars or anything like that, or even puddles that can stand on Mars. So just because the atmosphere is too thin.
I have a question about the telescopes. Almost all of us have seen pictures from the Hubble telescope. Kepler, the telescope and the project were designed to do a particular thing. Can you tell us what we are likely to see that might be relevant to this kind of study that might come from the James Webb telescope, which is the follow-on to Hubble?
Yeah, certainly. So James Webb is just, you should go look it up because it's a really cool looking telescope. It looks absolutely unlike any other telescope. It looks sort of like a giant gold daisy sitting on a cocktail napkin, but much bigger. And it's an infrared telescope, so it'll see out in the infrared portion of the spectrum where your human eyes cannot. And one of the things that it will be able to do that's relevant to these exoplanets is that it will be able to actually figure out what some of the atmospheres of these planets are made up of. And that's kind of the next step for figuring out whether they're truly habitable places, is looking at whether they have, you know, the balance of things that we would have in our atmosphere, or whether they would have even potentially what we call biosignatures, so the balance of different molecules in the atmosphere that indicate that there might be life influencing the composition of that atmosphere. So over the next several years, what you'll see from James Webb will be news about planetary atmospheres, which is really exciting.
I apologize first for being an exoplanet curmudgeon, but does your enthusiasm is it ever tempered by the awareness that in human culture, anytime a more advanced culture butts up against a less advanced, it's hard. It's the less advanced seems to take it pretty badly. Whether it's unknown diseases, or does that ever occur to you that might not be such a good thing?
No, mostly because the discovering of these planets has nothing to do with whether anybody from these planets is going to come here and infect us with alien plague. Like that I view as being largely out of my control, and I figure that space travel is so difficult that, like probably they'd be here by now infecting us with alien plague if they were going to. So, like that might happen, who knows? But, in the meantime, it largely doesn't prevent me from doing my job and figuring out what's out there. I would actually love to find, intelligent life in the universe. I'd love to find bacteria elsewhere in the universe. I would be very happy about that too. Even if I maybe keel over immediately and be like, this is great. So, I kind of just don't sweat it.
Thank you so much. Wasn't this be great? Help me in thanking Dr.
Thanks so much.
Very much. As Dr. Elness mentioned, we do have cookies and coffee afterwards. We encourage you to go over to the common ground and just enjoy each other and continue the conversation about what could be out there. Also, just want to call your attention, we had evaluation cards that were in the programs. We really appreciate receiving those. And also to see the upcoming thing that we have in January is a multi-day conference called Listen for a Change, Sacred Conversations for Racial Justice. And you can come to one or all three of those days. So there is a sign-up sheet if you're interested in receiving more information about that conference, because it is a little different than our normal events. But thank you again so much for being here.